All right, guys, we've officially made it to chapter 2. This chapter is going to be all about electric fields. Now, just a disclaimer, I was not I'm not particularly looking forward to recording this one because there's a lot of technical stuff in it, and it is, in my opinion and the opinion of a lot of people, the hardest chapter um, in electricity and magnetism, just because there's a lot of stuff in it. So I'm not sure how long this video is going to be. I'll try to be quick, but we're gonna just jump right into it. So, what is an electric field? So, I got this formal definition online, and I thought that it would be pretty good. So I'm just gonna copy it down. Okay, so the electric field at a point in space is the force per unit charge that a charge would experience at that point. So we're gonna explain why. I'm gonna explain why I capitalized would, but basically the electric field is a vector, and I guess to best explain it, let's go back to a force, electric force. So if we have a plus and a minus, right? We know by Coulomb's law that we need two charges in a distance to determine what the force of attraction is between these two. Now, here's the thing. This charged particle right here is always going to have the ability to attract something. Even if this guy were here, or here, or just completely out of the picture, right? It's still gonna have this thing, but it's no longer a force because there is no more Q, right there, no more Q2. So what would this be? Well, this is what people call the electric field. It's just some radiating, if it's a point-like charge, it is a radiating field, right? A hypothetical. So its dimensions would be just Q1 over R squared, or more formally, E equals F, the force, over Q naught, right? So what does that mean? That means the electric field does not depend on an external charge. It just depends on the charge of that particle. Okay. So let's look at the idea of of a point like particle. Okay. So if you have a positive point like particle, right? It's going to be radiating electric field outwards in all direction like this. Right? And we can examine any point around it, right? And these are just points in space. These don't have to be charged particles, right? Point P, Q, R, S, T, right? These are all just points in space. And if you'll notice something, if I draw rings around this guy, right, we'll see that the density, right, the density of these lines are getting further and further apart as we're going away. And that's attributed to this R squared right here. So the electric field gets smaller by this factor, okay? So that's an important point that I'd like to mention. So number one, electric field is always present, right? for a charged particle. Even if there's nothing that it's acting on, you can still calculate the electric field. Another thing is the electric field is a vector. So it has a direction and a magnitude. And yeah, so the next thing that I wanted to talk about also is the electric field in respects to the electric force. Okay, so we got the formula E equals F over Q. We also got the formula, from this formula we can get F equals QE. Okay, and remember, Q has a sign. Okay, so let's just pretend that we have this charged plate of pluses, right? And we have this particle right here. And let's call this particle a plus particle. Okay, it's just a point-like charge. We'll call this Q1 and this Q2. Don't worry about the fact that it's a surface instead of a point-like charge for now. We're just going to pretend that it's producing an electric field outwards. And that's also another thing that I want to talk about. If you have a positive point-like charge, they're going to be radiating outward. If you have a negative point-like charge, then the electric fields are going to go inwards toward it. And that is just a convention. You don't have to follow this if you don't want to, if you want to be a weirdo. Then you don't have to follow it. However, it will help you immensely in practice problems. And as you can see, this makes sense, right? Pretend these guys are in the same system, right? So originally they were in a different system that we'd put them in. But do you see how the arrows are going? It's showing that the positive charge wants to go towards the negative charge, and the negative charge, if you drew it the other way around, like I said, this is an arbitrary drawing, it would want to go to the positive charge as well. All right? So with that in mind, let's look back at this. So we have a positive Q and a positive a positive point-like particle, right? So we know that there's going to be a repulsive force. Now we're going to pretend that no force acts on the plate. We're only going to look at this particle right here. Okay. So I'm going to draw the force in. Actually, let me get rid of these first so that you don't get confused. I'm going to draw a force on this guy in blue. So this is the force exerted between the plate and this particle. The plate is exerting this force on this particle, right? Well, the electric field is also going to go in the same way, right? Because there isn't this induced field wants it to go away, right? Because they're both positive, right? So because this is has a positive sign, right? Then that means this F is going to be positive as well. So if the charge is positive, the E vector, and I'm putting the little arrow on top of the E, and the F vector go in the same direction. Right? And to be a little more precise, that means parallel or cosine 0 degrees. Okay, because the sine the cosine between these guys is going to be 0. Now, what if we had the same situation, but this particle was negative? Now notice, the electric field is still gonna be pushing this way. Like it's still gonna be this way, right? Because that's our convention of positive stuff, right? The positive stuff, it's radiating outwards. Okay. However, because this is negative, and notice that we are talking about the charge that it's being acted upon. So there's two concepts right here that I don't want you to get confused, and it might have gotten confused as I was talking. The electric field is always present, this would, right? However, we're looking, so in this case, like these points right here, these points don't have charge, okay? And yet it's still, there is still an electric field at that point, okay? Now we're putting force and electric field together to compare them. So this time, at that arbitrary point, there is going to be a charged particle. Okay, I just want to make that clear. So in this case, the charged particle is negative. Now, what direction do you think the force would be in? It would be in the opposite direction. Okay, does that make sense mathematically? Well, if we look at our little equation thing right here, yeah, it makes sense. Because if this guy right here is negative, then that means that the E and the F are always going to be the opposite of each other. So, to copy this statement, if the charge is negative, right? So I'm just going to directly copy and paste this. If the charge is negative, E and F go in the opposite. All right, so that means anti-parallel, okay, or 180 degrees, because the theta between them is now 180, okay? And this makes sense, right? So the E field is going this way, the force is going that way, and if we looked in reverse and we saw this guy, now this is getting confusing, and you can just skip over this if this confuses you, but if you see this as the thing making the electric field, you see how the electric field is going this way? It's going towards this negative particle, right? And how is the force going on this guy, right? It's going to be in the same direction. Why? Because the Q is positive, right? So hopefully that makes sense. I actually had to think about that for a little bit, but I think a better visualization, if we really want to go on to this topic, is having this guy as a negative Q and then this guy as being a positive one. So in this case, we would have the electric field going this way, and because this is a positive particle, the force would be going this way, and look, they're attracted, right? And if this was a negative Q and this was a negative dude, right, a negative particle, then it would be, the electric field would still be going this way, but the force would be going this way because it's the opposite. And see, it's consistent. It wants to go away, right? The force, they have the same charge, the same charge sign, and so this one wants to go away. These have opposite ones, so they want to attract each other. Okay, So that's an introduction to electric fields. And this guy's still out here. It's a little complicated, yes, but hopefully this makes sense. And if you want to comment down below, if you want a clarifying video, or if you just want me to answer some question in the comments about this, then please feel free to. And if you made it this far, that's pretty awesome. And yeah, that's it for the introduction to electric fields. Soon we're going to actually learn how to calculate them and different configurations of electric fields.